This is section 2 of chapter 6 of geometry, properties of parallelograms. Our objectives today are to use relationships among sides of and angles of parallelograms and to use relationships among diagonals of parallelograms. So first things first, let's look at this getting ready problem. It says use the information in the diagram. Which triangles are congruent? How do you know? So if we're looking at this diagram, we've got what looks to be a parallelogram. This big shape right here, and then some lines. I have these two diagonals going across, and so with those two diagonals, I see four triangles. I see one here, one here, one here, and one here. So we have to decide which ones are congruent. So let's think about that. Okay, this is a parallelogram. Then the sides opposite each other are parallel, and we see that. So this is parallel to this, and this is parallel to this. And if you think if they're parallel, that means that they never touch. They're like railroad tracks. They just run the same distance away from each other the whole time. And so if you think about that, since they're parallel, they're probably going to be the same distance because they're probably going to be cut in the same place by the opposite parallel line. So this is going to be the same as this, and this is going to be the same as this. Okay. Well, if two triangles have to be congruent, well, they should probably have the same length of a base. And so if I look in there, I've got this triangle BAE and this triangle DCE. And these two, they look pretty similar to me, so I guess those two would be the same. Then I've got this triangle BEC and this triangle DEA, and they look pretty similar to me too, with the same base. And even these other sides of the triangle look the same. So those are the triangles that I would say are congruent in this figure. And then if we also look at it, okay, we've got some bigger triangles in there. We've got this triangle BAC, and we've got this triangle DCA, and those even look the same to me. And then if we look at the other way, we have BAD, that looks to be the same as DCB right there. So in there I found 4 pairs of congruent triangles. Nope, I found 8, not 4. 8 pairs of congruent triangles. It's pretty... No, I did find 4. Oh, keep second guessing myself today. Sorry about that, guys. So, here we go. A parallelogram, you're wondering maybe what that is and how I knew that. Well, it's a quadrilateral with both pairs of opposite sides parallel. So we talked about that. Parallel lines are these lines across from each other. They're notated with these arrows. When I draw them on my paper, I just do that. And then these ones are parallel, so they get double arrows, so they're not confused with the other lines. All right. So our essential understanding for the day is that parallelograms have special properties regarding their sides, angles, and diagonals. We're going to learn some of these properties. Okay. In a quadrilateral, opposite sides do not share a vertex, and opposite angles do not share a side. So if I look at this drawing right here, opposite sides would be, well, side AB and side CD. Side AB, that's right here, it's opposite to side CD over here. They don't share a vertex. Now, opposite angles would be maybe angle C and angle A. They don't share sides. Angle A is made up of BAD, and angle C is made up of DCB, so they don't share any same sides. They're opposite from each other. Alright, so now you have that understanding. You'll notice in the theorems in the book, they abbreviate parallelogram with this symbol rather than writing the whole word out, and if it's plural, they just put an S in there. Alright. So, here's our first theorem. It says in a quadrilateral, if a quadrilateral is a parallelogram, then its opposite sides are congruent. This is actually a theorem about parallelograms. So this, if ABCD is a parallelogram, then side AB is is congruent, to side CD. These two are congruent. and side BC is congruent to side DA. It's as simple as that. So let's prove that. It says here we have a parallelogram ABCD. We are given that, we're given that it's a parallelogram. Using that information, we then need to prove that AB is congruent to CD and BC is congruent to DA. We're going to prove that those opposite sides are congruent. So, if we look at the first part of our proof, it says, the first part of our proof says ABCD is a parallelogram. Well, that, if we look into our, given, that was given to us. We can write that that is given. Now we look at the next statement. It says, let me just change the font of this so it'll fit. There we go. It says AB is parallel to CD. That's what that parallel notation is, and BC is parallel to DA. Well, how do we know that? They're saying that this side length AB is parallel to CD, so we could put the little hash marks in there, and that BC is parallel to DA. Well, that would mean that. How can you know that? Well, if you think about this is a parallelogram, what does it mean to be a parallelogram? It means that your opposite sides are parallel. So that is by the definition of a parallelogram. Definition of a parallelogram. Alright, next thing they tell us is that angle 1 is congruent to angle 4, and angle 3 is congruent to angle 2, so let's look at that in our drawing. Angle 1 is congruent to 4, and 3 is congruent to 2. Well, if you think about this, you have a parallel line here, and it's two parallel lines, remember? Cut by a transversal. You know a theorem about this. It is, see if you can find it or think about it. You know that if two lines are parallel and they are cut by a transversal, the alternate interior angles are congruent. There you go. Okay. Number 4 says AC is congruent to AC. Well, if something's congruent to itself, it reflects itself. That's the reflexive property. We know that. Alright. Angle ABC is congruent to angle CDA. How did they get that? Let's think about that. They're saying that these two triangles in here, ABC, is the same as triangle CDA. If you go back to congruent triangles, you may remember some different properties, some different triangle congruences. So there are something called angle, side, side, and angle, side, angle congruences. So let's see if any of those things work in here. Well, remember we said that 1 is congruent to 4, and 2 is congruent to 3. And look, they share the same base, so that's got to be the same. So they share a common angle on their base, a side, and then another angle. We can use angle, side, angle congruence to prove that then. Angle, side, angle. Alright. So the last statement that we're given is that AB is congruent to CD and BC is congruent to DA. So they're saying that AB, this line right here, they're saying that AB right here is congruent to CD over here, and that BC up here is congruent to DA down here, Well, if you think about that in the triangles, those are corresponding parts in a triangle. We know corresponding spots in a triangle are congruent. Therefore, that can be our last reason in our proof. Corresponding parts in a triangle are congruent. And there you have it. We prove this theorem. Alright, so angles of a polygon that share a side are consecutive angles. In the diagram, angle A and angle B are consecutive angles because they share side AB. So if we look here, we have A and B. They're consecutive because they share this side. Alright, from that we can create this theorem. X4, it says, if a quadrilateral is a parallelogram, then its consecutive angles are supplementary. So that's saying that A and B combined together are going to be 180. B and C are going to be 180. C and D are going to be 180. And D and A are going to be 180 degrees. So if we look at that in this picture right here, we have a lovely parallelogram right in there. It's kind of hard to see. Alright, it's called PQRS. So we know the angle S is 64 degrees. I'm just going to draw this a little bit bigger so we can actually see it. Now my drawing is pitiful, but stick with me. PQRS. They say S is 64 degrees. Alright, can you handle that? It says, what is the measure of angle P? Well, if we go back to that theorem we just talked about, it says consecutive angles are supplementary. If they're supplementary, they add up to 180. S and P, are they consecutive? They share a common side. Yep. That means together they must equal 180. So we know that, let's call this angle A, or this measure angle A, 64 plus whatever A is, has to equal 180. So if we subtract 64 from both sides, A then equals 116 degrees. That is right here. C. Alright, so say you're going to adjust the lamp so that instead of angle S being 64 degrees, it's now 86 degrees. Find the measure of angle R and PQRS. Pause the video now. Degrees. So the measure of angle R is 94 degrees. Alright, here's another theorem. It says if a quadrilateral is a parallelogram, then its opposite sides are congruent. So it's saying that if ABC is a parallelogram, then A is congruent to C, opposite angles are congruent, and B is congruent to D. So opposite angles, once again, are congruent. We are now going to prove this. So this is a multi-step proof. We'll see how we do. It says, given ABCD is a parallelogram, okay, prove angle A is congruent to C and angle B is congruent to D. So let's start on the top row and then we'll move down to the bottom rows. It says angle A and angle B are consecutive angles. Well, yep, we know that. And how do we know that? We know that by the definition of consecutive angles. That's what we said for our definition. Yep, that's true. Alright, so angle B and angle C are consecutive angles. Once again, that's by the definition. See if I can get that into a smaller font. Let's hang on one quick second. There we go, that'll work. Angle C and angle D are consecutive angles. Wow, that looks like another definition of consecutive angles. There we go. Okay, well that was pretty easy. Angle A and angle B are supplementary. Well, how do we know that? Let's go back and think about some of the theorems we proved. Look at theorem 6.4. It says if a quadrilateral is a parallelogram, then its consecutive angles are supplementary. So we know that consecutive angles are supplementary. Alright. Angle B and angle C are supplementary. Here's angle B, here's angle C. Same idea. Consecutive angles are supplementary. Alright, angle C and angle D are supplementary. Those are consecutive angles. We know consecutive angles are supplementary. That was easy. So now we need to get, how do they jump then to angle A is congruent to angle C and angle B is congruent to angle D? Well, if A and B are supplementary and B or C and C are supplementary, well, B is the same thing. What if you take that out? Oh, that would be then A and C are congruent. So we would say then supplements of the same angle are congruent. We have a theorem about that we've talked about before. Alright, here we have angle B and angle D are congruent. Well, angle B and C are supplementary, and C and D are supplementary. They're both supplementary to C, which means that they must be congruent. There you go. There's our proof. So what you're going to do now is this got it problem. Use the diagram at the right, given triangle ABCD. Prove that and that angle side AK is congruent to MK. Prove that angle BCD is congruent to angle CMD. Pause the video here and do that now. Alright, here's my proof. I know that ABCD is a parallelogram and AK is congruent to MK. That was given to me. Angle A, I remember I can't do all those fun symbols, so it looks a little funny, but angle A should be congruent to angle BCD. That's by opposite angles of a parallelogram are congruent. I notated that with the blue lines in there. Angle A is congruent to angle CMD. I haven't notated that with the purple lines in there. That's isosceles triangle theorem. Angle BCD is congruent to angle CMD. That's the transitive property of equality. And notate that with yellow in my drawings. There you have it. Alright, so theorem 6.6 says if a quadrilateral is a parallelogram, then its diagonals bisect each other. So, if ABC is a parallelogram, then AE is congruent to CE. Remember, if it bisects, it divides it in half. And BE is congruent to DE. Alright, so we're going to solve some system of linear equations, find the values of x and y and k, l, m, n. And then we're going to find km and ln. So, if this is a parallelogram, and it is, then I know that the diagonals bisect each other. So I know that Km bisects Ln. And through that, we can set up some equations. So we can set up so we know then that Kp must equal Mp. So y plus 10 equals 2x minus 8. Okay, we know that. And then we also know then that x equals y plus 2. Okay, so two equations I can deal with. So here's my two equations. Remember linear equations. We can use substitution to solve for stuff. So I know what x is. So instead of just sitting here and kind of look and I can figure this out. So I can put x in for y because I can put y plus 2 in for x because I know that x is y plus 2. So then I copy that first equation down, y plus 10 equals 2, and instead of 2 I put in that y plus 2, so I know x is y plus 2 minus 8. Now when I solve this I'm going to get y, and when I get y then I can use that to help me find these diagonals. So here's my actual equation I'm going to be solving. Just let me do a few things. There we go. Let's solve this. If we do some distributing, we then get y plus 10 equals 2y plus 4 minus 8. Alright. We combine our like terms, we get y plus 10 equals 2y minus 4 Now we combine our variables and our constants. We subtract y, we add 4, we add 4. This leaves us with y equals 14. Alright, y equals 14. Well, now let's find x. We then take this y equals 14 and we plug it back into our first one. For y, we get then x equals 14 plus 2. If x is 14 plus 2, x is 16. Now let's look at our drawing. We know that LP is x, so if LP is half of LN, that means that this half is 14 and 16. This half is 16. So LN equals 16 times 2, which is 32. We got our first one solved. KM is our next one that we got to figure out. We know that Y is 14. So if I plug that in, here's an easier one to plug it into. 14 plus 10 gives me 24, right? And that's half of it. So it's got to be double 24, which is 48. And there you have it. All right. Pause the video, do the same thing down here. Q is 10. You can check my work. If you think about part B, it says in problem 3, doesn't matter which variable you solve for first. Technically it doesn't, but there is always something that's easier to do because the second linear equation we wrote it was already solved for y. It's easier than to plug that in for y and solve for x to start off with. So it doesn't matter which one variable you solve for first, but sometimes the equation is more set up to solve for one first. So we've got a little bit more to get through. Here's theorem 677. It says if 3 or more parallel lines cut off congruent segments of one transversal, then they cut off congruent segments on every transversal. So if all 3 of these lines are parallel, all right, and they cut this line into 2 congruent segments, then the other line must also be cut into congruent segments. It's as simple as that. So here we have a figure. It says AE, BF, and CG and DH are all congruent, or all parallel, sorry. AB equals BC, which equals CD, which is 2. Alright. If EF is 2.25, that's this side right here. It's 2.25. What is EH? Well, using that theorem we just talked about, since all of this is cut into congruent segments, all of these must be congruent segments. If EF is 2.25, then each one of these must be 2.25. So we go 3 times 2.25. And what do we get? 6.75. EH is 6.75. Simple as that. Use the same picture in problem 4. Let me erase the drawings on it. EF is equal to FG, which is equal to GH, which is 6. 80 is 15. What is CD? Pause the video now and solve it. There you have my answer. Key to this one is that 80 is the entire segment that you see up there. So you need to divide that up into 3 pieces. If you divide that up into 3 pieces, you get 5. CD is equal to 5. And that is the end of section 2 of chapter 6. Sorry this one was so long, guys.